Is my voice audible? Am I audible? Okay, thanks. So we'll discuss today uh, some questions from week 3 of the deep learning course. Mostly what was covered was some continuation of the linear models and mainly support vector machine and multi-class version of it. So I hope you have gone through the video lectures for the week. So we'll just discuss some related problems. So in this first question, it is asked a data point with 5 dimension is given to us, and it obtains a score which is given by this vector. So we can see here there are, like, if it is a k dimensional vector, then we can say there are k classes, and it is a score for this given particular data point for each of the class. And it is asked find the hinge loss incurred by the second class with a margin delta of 5. So this margin is given as 5, and we are asked the hinge loss with respect to class 2. So, so we might want to recall what is the hinge loss function. So for class I, the hinge loss will be summation j not equal to yi max of 0 sj minus yi plus delta, right? This is the hinge loss, whereas j is the score for jth class, and what is yi? Y is basically here what is given is 2. So maybe I should write it here. Okay, I can write like this. Like this. This is for the ith data point. So here our ith data point, like there is only one data point which is given to us, and yi is the label for the ith data point. So we just need to put in these values. So sj is what? S1 is 18 minus, so our S2 is 20. 18 minus 20 plus 5 plus max of, so we won't consider for the second class, minus 5 minus 20 plus 5. So you can just continue this. This is equal to 7. So we just used uh, the formula for the hinge loss, and we need to remember that it is computed with respect to each of the classes. So here second class had the highest sort of score. So the loss is not very high for that class. If you may have considered some other class, the loss may have been much higher, like minus 15 or something. Because then this minus 15 would have been it should have been plus 15 everywhere. So here two terms had gone to 0 for us. But those would have turned out to be positive. And even these values would have become much higher. So we would have got a very high loss for the other classes. But for this 20 we got very less loss, and even for 1980 we might have got like less loss. So any doubt in this?
Sir,
Yeah,
sir,
yeah, please tell.
sir,
Yeah, I can hear you.
sir, repeat one more time, sir.
Oh, you want me to repeat?
Yes, sir.
So the question is asking like a five-dimensional one data point is given, which has these. This has the five-dimensional input feature vector, and this obtains a score of that is given by this vector. So it's a k. It's like if you have a k-dimensional score vector, that means there are k classes, and each of the entries is the score for each of the class. Now we have been asked to find the hinge loss incurred by the second class. So the hinge loss formula is this, where Sj is the score for the jth class. So we have been asked to find the hinge loss with respect to the second class, meaning we have to consider yi is equal to 2 for this particular data point I, and the delta value is also given. So you just need to know what is the hinge loss formula and what are the terms in it and what you kind of need to substitute in this. Is it clear?
Yes, sir. Okay, sir.
Okay. How many local minimum can be encountered by solving the optimization for maximizing margin of SVM. So if you remember, what is the margin of the SVM? It is like if you have some data points which are like assumed to be linearly separable, then our SVM finds a hyperplane which maximizes the margin between the two classes. So this is our separating hyperplane, and this is the margin. So if you remember from the lectures, uh, the margin is given by if your hyperplane is of this form, A transpose xi plus b, then the margin is given by 2 by norm of A. This is the margin. So maximizing 2 by this is same as minimizing, because this A and B is what we need to find. This is same as minimizing this or this. This is minimum of A transpose A. And we also have those constraints like A transpose xi plus b into y. This should be greater than 0. Or we consider like some one value, like we need at least this much. So if you see this, this is a quadratic function in A. So a quadratic function is like strictly convex, so it will have only one minimum. Okay, it will have only one local minimum. Is it clear? So answer is 1. Any doubts in this? Why we have to minimize A transpose A and not just A? So what we really need to do is we need to maximize this margin, but this is like not very easy. So what we do is like this function is not easily tractable, but this is same as minimizing. This is same as minimizing mod A. Like maximizing this is same as minimizing the norm of A, and minimizing the norm of A is same as minimizing the norm of A square. Norm of A square, and norm of A square is equal to A transpose A. So essentially we are minimizing this, which is a quadratic function. Like you cannot just minimize A because A is a vector. This is a real valued quantity. So you can't compare two vectors as A less than B. If these are two vectors, you cannot really use this sort of comparison. So you can't say if this is the minimum or this is the minimum. For real valued quantities, you can say what is the minimum. You can say norm of A is less than norm of B. But this you can't say. A is less than B. You can say if A comma B is some d-dimensional vector, then you can't say A is less than B or something, but you can say mod A is less than mod B. The norm, L2 norm. Is it clear? Okay. So they're asking which of the following classifiers can be replaced by a linear SVM. Uh, so we have been given like three different kind of models: logistic regression, neural network, and decision trees. So logistic regression is a linear model, just like SVM. Neural network is non-linear. Decision tree is also non-linear. So we can say like we can replace a linear SVM with logistic regression because both are uh, linear models. Only the difference is instead of hinge loss in that we use in SVM, in logistic regression you use logistic loss. If you have done a machine learning course prior to this, then you may be familiar with this. Non-linear. Any doubts? Here it is given a support vector machine defined by W transpose X plus V equal to 0 with support vectors xi and corresponding Lagrangian multipliers alpha I and the class value is yi. Which of the following is true? So the Lagrangian multipliers is given, class value is given, and these are the support vectors. So if you remember um, the way it was derived in the lectures.
Option D, sir.
Sorry. We are saying answer is D. Yeah, it seems all options are correct.
Option.
So maybe I'll just try to derive how this comes. So you wanted to minimize this function. So for sake of simplicity in computation, you equivalently minimize. You want to find. Okay, you can use W here because here there is W to minimize this. This same as minimizing half of W square, and there is a constraint that W transpose X xi plus B to yi. This should be greater than equal to 1, right? For all I. For all I in your data set. Okay, so when you have this kind of constraint optimization problem where you have to minimize some function f of x constraint to some cix greater than 0, then you find the Lagrangian, which is f of x minus lambda, or you can say alpha cix summation, where alpha is greater than equal to 0. This is the Lagrangian. So the Lagrangian that you get here is W minus summation alpha and for optimal W, the partial derivative with respect to W and with B, this will be equal to 0. So what you will get is W minus alpha I yi xi. So summation I alpha I yi xi. I took the partial derivative with respect to W. So this is, and this is what alpha I y summation. So from these two, what we get is w is equal to summation alpha I y xi and summation alpha I y is equal to 0. So if you substitute this 2 into this, what you have is n is equal to 1 by 2. You have to take this into this. So an easy way to do this is, if you look at this part, what will come out here is ij alpha yi xi alpha j ij is j alpha j, I think I should write alpha j yj xi transpose xj minus summation I alpha I yi. This w will again, and separate this stuff, this w will again become summation alpha I yj alpha j yj xj transpose xi plus, sorry, minus alpha yi b minus 1 minus alpha y. So basically, because summation alpha y is equal to 0, these two terms go to 0. Okay, sorry, here there is no y, only this term will go to 0, and this is positive. And if you see these, this term and this term is same, only there is one half factor here. This is alpha I minus alpha I 1 by 2 times alpha j yj. So what we did is, so this is the C option, this is the A option, this is the A option, B option and C option. We use the Lagrangian to get what will be the optimal values of W with respect to the Lagrange multipliers, and then we substituted those values into the Lagrangian equation to rewrite it in terms of the Lagrange multipliers. So the final optimization problem that your solver does is basically finds uh, like maximum alpha, or you can say argmax alpha star. What a solver basically does is finds the value of alpha which maximizes your Lagrangian function in terms of alpha. Once you have this alpha values, you can use this alpha values to compute your W, because W is alpha y x and you know y and x. Okay. Any doubts in this? Okay, I guess this is clear. So here we have been given a two-class classification problem of two-dimensional feature vectors. The support vectors and corresponding class label and Lagrange multipliers are provided. Find the value of SPM weight matrix W. So here they have already solved and given us the alpha values for each of the data point. So then to find your W value for the SVM, it is, since it's a two-dimensional feature vector, your W is be two dimensional, and W is equal to summation alpha ya x. Here just three values. So it is 2 into minus 1 into minus 1 comma 1 plus 1 into 1 into 0 3 plus 1 into 1 into 0 minus 1. So it is 2 and minus 2 plus 3 minus 1. That is 0. So B is the answer. Is it clear? Okay. Suppose we have one feature x in R, so one dimensional feature, and binary class y, two classes. Dataset consists of 3 points P1, P2, and P3. Which of the following is true with respect to SVM? Let me just draw this and something like this. it's one dimensional. 0, 1, -1. So I have first point -1 here belongs to -1 class. One point here +1 class, and this also +1 class. Okay, P1, P2, P3. So if you see, your maximum margin is this, right? That is separating the -1 class and +1 class. And what will be your support vectors? This point P1 and P2 are your support vectors. So what are the options? What are the options asking us? Maximum margin will increase if we remove the point P2 from the training set. So if we remove this point P2 from the training set, we will have this -1 point P1, which belongs to -1 class, and P3 0, 2. So then our margin will shift, like our decision boundary will shift. So here the margin was this much, but here the margin will be this much. So our maximum margin is increasing. So A seems correct. Let's look at the other options also. Maximum margin will increase if you remove the point 3 from the training set. So if you were to remove the point 3, if you just forget about this point, still your decision boundary will be here only and margin will be the same. So this is incorrect. Maximum margin will remain same if you remove point 2 from the training set. So that we have just shown by removing point 2, the maximum margin is actually increasing, it won't remain the same. So this A option seems correct. Any doubts? Okay. So in this question they are asking, if we employ SVM to realize two input logic gates, then which of the following will be true? two input logic gates, I think, and they are asking AND gate and OR gate. So that means if you have AND gate is what? If you have like 1 and 1, this is your X. X1, X2, Y. So if it is 1, 1, it should be 1. If it's 1 minus 1, it should be, and right here 0. So 1, 0, then it should be minus 1. If it is 0, 1, it should be minus 1. If it is 0, 0, it should be minus 1. This is the AND. OR is 1, 1, 1, 1, 0, 1, 0, 1, 1, 0, 0, 0. So this we all know. So we, like in both the cases, we are having these 4 points. 0, 1. So we have 1 comma 1 here. If we consider the first case, then we have this 0, 0, 1 comma 0, 0 comma 1, and 1 comma 1. This is the plus 1 plus, and all. So this dot is plus 1 cross, and this is minus 1 cross. So your decision boundary should be something like this, and this will be your maximum margin, something like this, right? This is your decision boundary. Similarly, if you were to do it for the OR gate, we have 1 comma 1, okay. So you will have a decision boundary from here given by the SVM. So what are they asking? The weight vector for AND gate and OR gate will be same. So if you see the weight vector, it has 2 components, right? W and B. So if you suppose this was some W1 comma B1, then even if I scale it like K times W1 comma K times B1, still it is, these two are same decision boundary, right? But that's just not the only thing. Even if this is W2 comma B2, if you see the direction that you get, the W vector, which is perpendicular to our decision boundary, the vector perpendicular to our decision boundary, that may be same, but the B may be different for these two classes because it is shifted. This, if you shift this above, then you get the AND gate. So the weight vector will not be same. The margin for AND gate and OR gate will be same. So the margin, if you see, it is this distance, and this will be same, right? This is just these 2 points and this, and here also you have these 2 points and this. So the margin will be same because your W direction can be same. W direction is same, then 2 by W, this will be same. So your margin vector can be same, or it will be same. Not the margin vector, the margin value. Margin and the weight vector will be same for AND and OR gate. So the B will not be same because B has shifted. So we can say B is the answer, right? Because the last option is saying none of the weight and margin will be same. But we know margin is same. Okay. Any doubts in this? So the weight vector completely won't be same because this B is also part of your weight vector. No? Yes, bias. The bias won't be same here. I mean, if you up like consider vector feature vector appended as x, and this one vector also, like features are x1 x2 1, then you can, another way to consider is this W transpose. If this is your new feature vector, then this is also your, this is your boundary. So here W becomes three-dimensional, where the third value is actually your B, something like this. So both W and B are sort of parameters that you need to find out. I think the language can be confusing as to what exactly weight is. Okay, so you are saying because it is only weight vector, you don't want to include B in it. So if you don't include B, then the answer will be C. But if we include B, then the answer will be B. I mean, there is no one right way to do this. Like your interpretation is also right, and that there is you can interpret in different way also. So in a way, you are right. Like in that sense, if you are not including b, then the weight vector is same. But if you consider b also as also part of the weight vector by doing this kind of thing, then uh, like b will be the right answer. Okay. So we'll go to the next question. The value of Lagrange multipliers corresponding to the support vectors can be. So if you look at the Lagrangian function, what you have is minus alpha, right? So here your alpha is greater than equal to 0. So for the support vectors, so alpha is are all greater than equal to 0 when you have inequality constraint, because you have this inequality constraint, right? B minus 1 should be greater than 0. So option A is incorrect. And we have been asked the value of alpha corresponding to the support vectors. So let's just try to understand what is the role of the support vectors. So if you had seen in a previous example, we had a point here and a point here and a point here. So our hyperplane decision boundary was drawn by this. This was not really influencing whether it is there or not there, or didn't have a role in determining W. So your W was, how do you get it? You get it by alpha I by xi. So here your alpha i's are of two types. One is alpha I is greater than 0 and other is alpha I is equal to 0. So your alpha I is greater than 0 So alpha is equal to 0 are like they are not taking part in finding decision boundary, because alpha equal to 0 means those points are not in this summation. The remaining alpha greater than 0, they are there in the summation. So they are the support vectors. This is one way of interpreting it. So for your support vectors, your Lagrange multipliers are greater than 0. It's not any real number and it's not any non-zero number also. For your support, if you look at this part, for your support vectors, this term yi minus w transpose xi plus b minus 1, this will be equal to 0 for your support vectors, but alpha will be greater than 0. And for your uh, other data points which are not support vectors, alpha will be equal to 0, but yi w transpose xi plus b will be greater than 1 because they are here. Okay, so this condition, like when this is 0 this is positive and this is 0 this is positive, this is called as complementary slackness. I think it comes from this Farkas lemma in optimization, if you have done an optimization course, or you can maybe read this numerical optimization book. You can read that constrained optimization. Constrained optimization. You can read about Farkas lemma and this Lagrange multipliers and everything in there. I think in the next week, some optimization introduction, like some part of optimization is necessary for neural networks, will be covered in the next week's lectures. Okay, any doubts? Okay, there is no doubt. I'll go to the next question. For a two-class problem shown in figure, which are the support vectors x, y for an SVM classifier? So these are the two classes in blue and red. So this will be our decision boundary. I'm roughly drawing it. Maybe a good way to draw will be if I consider the midpoint of these two. Midpoint of these two. Okay, this will be our decision boundary. And these are our support vectors, right? Now it may be confusing as to whether both of them will be there or not. Or is it only one? Because if we consider only these two, then it will go from here. So I guess these three will be there, right? Okay. Any doubts? So what are the points? 4 comma 3, 4 comma 5 and 7 comma 2. Okay. Okay, I'll go to the next question then. This was straightforward. Uh, what is the equation of decision surface using SVM? So what we can do is we knew what were the points, right? These are the points. We have been asked the equation of the decision surface. So the points pass through this and midpoint of. So what is this? The midpoint of these two, and this is the midpoint of these two. So our decision boundary passes through this line. So we just need to find the straight line which passes through these 2 points. So what are these 2 points? One is 4 comma 4 and the other is 5.5 comma 2.5. So we need to find the straight line which passes through these 2 points. do is y minus 4 is equal to 4.5 minus, sorry, 4 minus 2.5 upon. So what I have is x minus y plus 8 equal to 0, right? This is the line. Is this correct? Oh, sorry. This should be x plus y minus 8. Yeah. So in this, using only the support vectors, we found the decision boundary. So if there is no doubt, I'll go to the next question. Just interrupt me if you have any doubt. Find the margin using SVM. So to find the margin, what we need to do is we have this straight line, what we found, x plus y minus 8 equal to 0. Now what we need to do is this is my f of x, let's say, and I had my points, right? 4 comma 4 comma 3, 4 comma 5, 7 comma 2. So when I substitute a given class, I should get, they should lie on the this point, right? So if this was x1, then f of w comma x1 should be equal to 1 for, let's say, this point x1, x2, x3. This is plus 1 and this is minus 1, and f of w comma x2 should be equal to minus 1, should also be equal to minus 1. So let's just see if this happens. If I substitute 4, 3, I get minus 1, right? 4, 5, I get plus 1. 7, 2 also I get plus 1. So that's okay. It's like you just flipped the signs. This became class plus 1 and this became class minus 1. So it is satisfying this. That means I can just do 2 by norm of w to find my margin. That is 2 by root 2 is equal to root 2. Okay. Any doubts in this? So what we were saying was, for the points which are on the margin, it should be, for one class it should be plus 1 and for the other class it should be minus 1. So we have the constraint, right? yi w transpose xi plus b minus 1 should be greater than equal to 0. So the points, the points where which the points for which this is equal to 1, that those are our support vectors where this equality holds. So this was our, these are the support vectors that we got, x1, x2, x3. So for the support vectors, yi into this should be equal to 1. So if I consider uh, x1 as yi equal to minus 1, then yi into f of w comma x1 is equal to 1, where f of w comma x1 is this thing, this term. This is y1 equal to minus 1. Is it clear? Okay. Okay, this is mostly the question that I got for today. If you have any doubts, you can ask, or otherwise I can discuss something else. Okay, if there is no doubt, then maybe I can briefly discuss about something called a soft margin SVM. I think that was not covered in the lecture. Is it covered? Soft margin SVM is not covered, no? So I think what was covered in the lectures was hard margin SVM, where you where your data is sort of separable, and you find this strict margin which separates your data points. This is the hard margin SVM. In soft margin, what is considered is you have your data point something like this, and there is something like this. There is a circle here. So if you see, it doesn't completely, it's not completely separable because some points are over here and some points are over there, and you can't find a strict boundary like this which totally separates your data. So you try to find something which which classifies most of your data points. That is called as a soft margin SVM, where you may have some support vector like this, and these are also your support vectors which are to the left of it. This is referred to as the soft margin SVM. So how in the hard margin SVM you wanted to minimize uh, this, right, such that yi into w transpose xi plus b minus 1 greater than 0. This is greater than 1. This was your hard margin. So what will happen is, if your data is like this, you will never be able to find your w and b such that this constraint is satisfied. It is impossible, because if it is satisfied for this, it won't be satisfied for this. If it is satisfied for this, it won't be satisfied for that, because each class data point is kind of mixed, very close to each other, some points. So in the soft margin, what additional is done is, maybe I just copy this thing. Additionally, so here you are trying to find the w and b, which minimizes this, satisfying this constraint for all I in dataset. Here also w, b. what you do is, instead of imposing this strict constraint, you put uh, a slack variable. This is called a slack variable, and this ii is greater than equal to 0. So you have two new constraints. What this constraint is saying is, if you remember, in the hard margin case, okay, there's some doubt. Soft is also, this is also a linear equation only, but we are allowing some misclassifications to happen because there is no other way. But we want to minimize the number of misclassifications that are happening. At the same time, we want to find some sort of like maximize the margin also in some way. Okay, so in this kind of case, like you can draw something like this also, this red line, but it doesn't seem to like maximize a margin in some abstract way, intuitive way. While this green line, it seems to like separate the data more well. Okay, so here what we have done is, okay, this is not the complete thing, this is one thing that you do. So let's just see what happens when you add this thing. When I have added this thing, if you remember, in the hard margin case you had the support vectors, and for the support vectors you had this condition yi, maybe I'll write in red, yi w transpose xi plus b is equal to 1. That is, if it is in this class, this value is equal to 1. If it is here, this value is also equal to 1 for your hard margin case. When I have done the same thing, y w transpose xi plus b equal to 1 minus psi I. So this psi I, if you see, it is different for each of the samples. For each I it is different, and what it is doing is, it is allowing some samples to come inside of this. This is the line w transpose xi plus b equal to 1. That is this line, and this line will be w transpose. Let's suppose this is this line, and this line will be w transpose xi plus b equal to minus 1. Okay, this is line minus 1, this is line plus 1. When you multiply yi, which is the sign of xi, like label of xi, this term will become plus 1, which will also become plus 1. So these are the two lines. So when I am doing this minus psi I, where psi I is some positive value, what I am doing is I am allowing some points to be in interior of your margin, where psi I is different for different xi. So for some xi you may allow this much, for some xi you may only allow this much, for some you may allow this much, like that. But you don't want to allow too much. So to restrict that, you add one more term here, c summation I psi I, where the c is a hyperparameter. C is a hyperparameter which you have to choose. You have to choose what value of c you want to use. If you give a very high value of c, that means it will give a lot of weightage to this psi i's, and it will not allow psi i's to come into the interior. It will try to minimize how much slackness you are allowing the points. If you use a very low value of c, then it will, if you like set c very close to 0, so the c parameter has to be greater than 0. But if you set it very close to 0, some 0.0000010 power minus 6 or something, then it will give very low weight to the xi values. That means it will allow like big slackness, like even this red line may find this red line where you have points coming like this, something like that. On the other side, it may allow too much slackness. I hope I'm getting the point across. So this is your soft margin SVM. So the changes that were made was this and this. If you add these things, then it becomes the soft margin SVM. This is more used in practice in compared to hard margin SVM. Magnitude of margin. Magnitude of margin we want to minimize, like same as the you have one more parameter. So same as the case of hard margin, you want to maximize the margin. You want to maximize the margin at the same time. So when you maximizing the margin, you are allowing, like in the case of soft margin, if you increase the margin, like if you increase the margin to like something like this, then you are allowing more points inside this. So the psi value will increase if you increase the margin too much. Increasing the margin means decreasing W. To decrease W too much, then the psi values will increase. But if the weight C that you're giving to psi value is too low, then it may accept it. But if the C parameter is very high, if C is some 10,000 and your W is very low, W is very low is meaning the margin is very big. Margin is something like this, and your data points are, lot of data points are here. So all these xis will get counted. This plus this, let's say this is psi 1, psi 2, like this all will get counted. Here also it will add for x. All this will be summed over here and into 1000. That is a very big value. But your objective was to minimize this total thing. So it may find some W star which is not too small also, not too big also, and it maybe it finds your, like this is a decision boundary, and maybe it finds margin something like this where only small points are there inside the margin. If you are using a very high C, so the C parameter is kind of difficult to tune in the soft margin SV. If you want to read more about it, you can. There is a book by Peter Flack called Machine Learning. In that book, you can, and there is a very good explanation, intuitive explanation, and I want given for this. Okay. So anything else? Any doubts in this or anything that was covered in class or anything that we discussed today? I think less people joined today because of Independence Day. So Dr. Kokate, are you a professor somewhere? Okay, where? You can unmute also if you are able to. Maybe I just wait for a few minutes till 7:40. If you have any doubts, you can ask, or else I'll close the meeting. I'll just wait for a 1 or 2 minutes. If you have any doubts, you can ask, or else I'll close the meeting.
So my question
Yeah,
is how to proceed with the soft
sorry.
margin SEM to minimize the errors. How to minimize the error in soft margin SEM?
How to minimize the error?
Hmm. Is there a methodology to reduce the errors? Right?
Yeah, so these you can say these are like error terms. The psi values. The psi is actually max of 0 comma 1 minus yi w transpose xi plus b. So if you see, this is quadratic in w and linear in psi I.
Correct.
So this can be solved by if you are aware of some optimization tools, so they have,
Optimizing the W or optimization of W will help us.
yeah, you need to find W, B, and xi also.
All together.
Yeah, such that all
Okay.
these constraints are satisfied.
Correct.
So if you have familiarity with some optimization solvers, then there is interior point methods which
Mhm.
do quadratic optimization.
Correct.
Or else, if you there are some packages called scikit-learn which have already implemented this whole thing, where you have to give your data and they will
Okay.
give you these parameters.
Thank you.
Yeah, thanks. Okay, then I'll close the meeting. Durga Prasad, you have anything to ask? Okay, then I'll close the meeting.